Welcome back to lecture 14.3, where we're going to talk about a new kind of thing, which we're going to call a heat pump. Okay, so far we have thought about our Carnot cycle as having an engine, right, where we had heat flow in, we had heat flow out, and we produced work, right? So this was our heat engine. We also had a refrigerator, where we had essentially the same thing, a refrigerator, but we ran it backwards, right? We put work in, and that extracted some heat and dumped it to some high temperature. Now, remember, what we did was we said, in this case, in the refrigerator, we wanted to make the cold body colder, right? Or keep it at the same temperature when there was external heat coming in. So we wanted to extract some heat. So here, our efficiency of an engine was 1 minus, let's write it in terms of what we want. We wanted work, right? But what we put in was QH. And this ended up being 1 minus TC over TH. Here in the refrigerator, we didn't call it an efficiency, we called it the coefficient of performance, because what we wanted to do was extract the heat, but what we put in was the work. And this ended up being TC over TH minus TC. Now, I can do one more thing, and I'm going to call it a heat pump. And it's going to look identical to the refrigerator, right? So let's call this one a heat pump. We're still going to have to do some work, extract some heat, and dump some heat. But now, I'm thinking about this same object, but not about what I want is to get it cold. I want to dump as much heat to the room, to my hot reservoir as possible. That is, think of the refrigerator in your house not as a thing to keep the stuff inside as cold, but now as something to heat your house. Could you, it's dumping heat into your home even all winter long, right? Are we doing something interesting, right? So imagine the following. You take and fill up a pitcher of water from the tap. It's at a certain temperature. You put it in the fridge. Now this you had to extract that heat. Your system had to do some work to extract that heat, but then it ended up dumping heat to the room. So you really took some heat out of the cold object and dumped it into the room. This is why it's called a heat pump. It pumps heat from a cold object to a hot object. Okay, so how do we think about the coefficient of performance of a heat pump? Well, what do we want out? We want out as much heat as possible, right? But we're putting in work. So this is going to be QH, or QH minus QC, or TH minus TC. Okay, so again, so this is always less than or equal to E1. This could be 0 if the temperature here were very, very small, right? So but this is always greater than equal to be 1, right? And it would only be 1 if Tc were at absolute 0. Okay, so our heat pump, you can see, is more efficient when we have a small temperature difference. A lot like our fridge, right? It's also more efficient when the high temperature is high, or more higher performing if the high temperature is high. So, why is it, for example, well, now what I want to do is, this is our concept of our heat engine. I want to actually go through in class, live, and we'll do an example where we calculate. We've already calculated the efficiency of, say, the boiler. We can do an efficiency of a refrigerator, an example, and we'll do an efficiency of a heat pump, or performance of a heat pump example. In that example, we're going to have to introduce something, right? Because instead of just cooling down a jug of water, maybe it's more interesting to think about transforming water into ice. Okay? So we remember we had the cooling of water was quite efficient because the heat capacity of water. So for water, the heat capacity was quite large. It was 4186 joules per mole K. Sorry, joules per kilogram. That was C. Joules per kilogram. But the one issue here is, we just get our water cold. Maybe we can do something else. Maybe we could even cool it, and we could freeze it. So if everybody remember what happens when you freeze at a phase transition, you change the temperature. Sorry, at a phase transition, you change, from liquid to solid, but you don't change the temperature. So if you imagine this freezing process, you also have to introduce something called the latent heat. Okay, so we'll use that a few times. So our latent heat is how much heat you have to extract per unit mass to do this process, right? So for water, the latent heat of freezing, so that's what that F is 334 kilojoules per kilogram, right? So this is 4.1186 kilojoules per kilogram. This is 334 kilojoules per kilogram. So if we want to make a heat pump where we have to extract a lot of heat, right, and dump it to our high temperature environment, well, it probably is better to do a freezing process than it is to just do a cooling process. Okay? So in our in-class example, we're going to freeze a kilogram of water and see how much heat we dump to our room. Okay? All right, so that is the end of lecture 14. And now we have basically covered chapters 1, 2, 3, and 4, and parts of 7. And now we're ready for a midterm review and the midterm. Okay, so next time, midterm review.